Ch6 already told us, teach us how to do that. Okay? I generate small wave at the interface, and then all this I can find out. Okay, this is the dispersion relation. I can find out the complex potential, right? Stream function. Okay, all this. Okay, I think I did that. Okay, already we did that already. Okay, so all this can be applied to here. Okay, so we do the similar thing here, as you can see here. We go back to our this. Okay. So we introduce this small perturbation into this flow system and try to evaluate what's the flow field inside this flow system based on this small perturbation at the interface. Okay, and here we can start from try to guess. Okay, as you can see in the textbook, as you can see, this is our perturbation at interface, and what you say is what? Since as you can see here, this is in x direction. In x direction, we have I 2 pi over lambda x. That's a sine cosine function. So that means in x direction, divided by this, in x direction should be triangular function in x direction for the solution. Okay, so satisfy this carbon equation. Okay, and then for the y, because you have the phi is a function of x and y, right? Since you try to evaluate this carbon equation with all the boundary conditions. So this is the carbon equation, and carbon equation, this phi is function of x and y. Okay, and in the y direction, what happened? Y direction should be its potential. What? Should be its potential decay. Okay, depend on the y should be depend on its potential either decay or growth. Okay, and as you can see, so y in the y direction should be its potential function. So from here, so they have this. They can give you this. This is the solution form. Okay, should be equal to our in y direction we have its potential y here. Okay, and then in x direction we have the sine cosine function that's become its potential I 2 pi over lambda x minus sigma t here. So that's from the textbook. Give you the solution form. Okay, should look like this. Okay, and here he mentioned you can use in so-called separation of variable, right? Separation of variable to solve this physical problem. And the carbon equation we have is what? Is this, right? Gradient phi I is equal to 0. That's a carbon equation. And by using the separation of variable is what? We try to separate our x and y into two functions that called the separation of variable, right? In your engineering mathematics. So once you evaluate this, is the capital X is function of x only, capital Y is function of y only. So here the plus phi I is equal to x double prime times y plus x times y double prime equal to 0. Okay, and you have a case 1 and case 2 to kind of discuss. Okay, for example, I change it become like this. Okay, x double prime over x equal to minus y double prime equal to a squared. This constant is a constant. Okay, I can evaluate this. Okay, and once you use the case 1, okay, you have two ODE to solve, right? X double prime is equal minus a squared x, and the y double prime plus a squared y. And x this is ODE give you the solution form is potential function. Okay, and this ODE here give you the sine cosine function, right? Sine cosine function because of y. Okay, and then you can also try to discuss the case 2. What the case 2 mean? Case 2 means is instead of minus sign here, we can change the minus sign here. So minus sign here, I have to switch this, right? This is the minus, and it become positive. So by doing similar thing here, I try to evaluate this x function. X function become sine cosine function because this is a characteristic value for this. And this is y become its potential function. And which one do you want? Which case would you choose for our physical problem? Which case? Case 1 or case 2 should you choose? Which one? This we have, if you're using a separation variable, we can have this solution form and this solution form. Just switch, right? One is a potential function, one is a triangular function. Okay? Which one you should choose? That's need a physics, right? Physics give you what? When y go to infinity, our is potential decay because our amplitude, okay, small amplitude perturbed here. This small amplitude in the far field should vanish. Okay, so that means in the y direction should be its potential decay with. Okay, so which case should we choose? Case 1 or case 2? We have from this equation we can have this solution. Case 2, case 1 or case 2 solution. Because the case 2 is y is its potential, right? Its potential function. Okay, and then case 1 y is a sine cosine function. Since I perturb here, as you can see, in x direction the solution form should be sine cosine function, right? In the y direction should be its potential function. Because okay, so we should choose this case 2. This solution form. Okay, once you select the case 2, as you can see, our x function, x, okay, this x is equal to sine cosine function, or this equal to this, and y here is equal to its potential function, right? Okay, so you choose a case 2. This is our case 2. Okay, x is our sine cosine function, y is its potential function, and our phi is what? Phi is x times y, right? These two functions. So we have this is x, this is y. Okay, and we apply the far field boundary condition. As you can see, v is a partial phi I partial y approach to 0 when y equal to minus infinity. Right? When this perturbation, because phi 1 is a perturbation velocity potential, right? Phi 1 should be eventually disappear, because this phi 1 only have a very near the interface. When far away from this, it will be recovered back to our free string. Right? So the velocity generated by this perturbation, this v should be also disappear. So this is the boundary condition in the far field, as you can see here. Okay, so for the phi 1 interface below here, phi 1 here, we have to apply this. When y go to minus infinity, our partial phi 1 partial y should be approach to 0. So I do that. V is equal to partial phi I partial y, phi 1 partial y. This is our phi 1, for example. Okay, so this is when I do that, this is take the partial derivative with respect to y here, right? So become AC1, A is potential AY minus, because minus A here, minus AC2 is potential minus AY here. And this, since y go to mass infinity, this is y go to mass infinity, this term here will be what? Is potential decay, because y go to mass infinity. So this is finish or disappear, because y go to infinity, mass infinity, this term will be dropped. Okay? And our equation become like this, right? This term multiplied by this term should be equal to 0, because our velocity should approach to 0. So what you can say, since this is arbitrary value, this is arbitrary value, this is also arbitrary value, right? And when y go to minus infinity, this becomes exponential growth. So only constant we can make this equal to 0 is our C2. This constant should be equal to 0. Okay, C2. So our phi 1 here, C2, this constant should be equal to 0. Because when y go to minus infinity, this eventually will go to 0. So our constant here, only the C1 left, right? C2 go equal to 0. So this term, so only C1 left. and C1 can multiply by B1, give you another constant D1, and C1 times B2 give you another constant D2. So that's our V1. Okay, that's our velocity, perturbation velocity potential. Okay, should look like its potential, okay, function in the y direction and sine cosine function in x direction. Okay, vice versa, similar discussion. V2 here we have this, right? V2 if I x and y is equal to this, and our boundary condition just become y go to infinity. So y go to infinity, partial V2, partial y should approach to 0, and this term here evaluate partial V2, partial y, as you can see. When y go to infinity, this term, okay, automatically, okay, its potential decay, so that will be disappear. So only this term here, when y go to infinity, this term have to be equal to 0, and this constant have to be equal to 0. Okay, and C1 have to be equal to 0. Okay, so in the V2, okay, our solution form will be its potential minus AY, okay, and then this is our sine cosine function, okay. Okay, so that's how you guess, okay, from this discussion you can guess, okay, in the V1 and V2, okay, the velocity potential below and above, okay, the solution form should look like this, okay. And we already know our perturbations is like this, right? So this perturbation only introduced in the, okay, small traveling wave at the interface, right? So as you can see here, as from this kind of the discussion here, we can guess, okay, we can guess what? This acceleration sine cosine function should be very similar to our, okay, perturbation. So our solution form will be eventually, only the difference is what? This we have its potential AY in the V1, its potential minus AY in V2 here. Okay? So we can guess our solution form. In V1 we have its potential. Okay, this is AY and this is sine cosine function. And V2 we have a constant times its potential minus AY times our sine cosine function. Okay, and this sine cosine function will be exactly the same our traveling wave solution form of our perturbation. Okay, so from in the textbook it's written very simple, right? It just gives you the, okay, using the separation of variable, and then so from the in view of at the interface, this interface is a triangular function in x direction, and the y dependent function should be its potential, and so they can guess their solution form should look like this. Okay, but that's behind the story is like that. Okay, that's it. Okay, so until here we get the solution form. Only turn left is what? Is A1 and A2, right? We try to evaluate A1 and A2, and then based on our boundary condition. Okay, and this from the boundary condition we can get our A1 and A2, and then finally we can get the velocity potential. Okay. Okay, first we try to use in the kinematic boundary condition. This is kinematic boundary condition, right? Partial V1 partial y is equal to partial A dot partial t plus U1 partial A dot partial x. So we have A dot here, so we take the derivative with time, and for this function, and also derivative with x for this function, and our V1 is here. So I take a derivative V1 with y, and evaluate the y equal to 0, and then I can equal using this function to find out my constant A1. Okay, my constant A1. So A1 you can get, this is A1, you can eventually get. This constant should be equal to I epsilon times minus sigma plus U1. Similar, we have a kinetic boundary condition for the V2 here. Okay, we have a V, so similar here, and V2 here. Right, and then by using this equation, I can get this A2. This A2 should equal to this. Okay. Okay. So when I get the A1 and A2, I'm substituting back to this solution form. So this is A1, right? Times this. This is V2 is equal to A2 times this, right? So this is our what? okay, velocity potential, okay, for this system. What kind of flow velocity potential? Once you have a perturbation at the interface, right, and this perturbation causes our flow field, okay, will slightly change like this. Okay, we call this is perturbation velocity potential. Okay, so we apply the kinetic boundary condition here. The final boundary condition we didn't apply is what? We didn't apply is a dynamic boundary condition, right? So dynamic boundary condition is from phi1 for this and from phi2 at the interface they should be equal. Okay. Okay. So I have the phi1 here and phi2 here. So this is all we can evaluate partial phi1, partial t, right? Partial phi1, partial x. Okay. And then we have a phi2 here. I can evaluate partial phi2, partial t, and partial p2, partial x at the interface when y equal to 0, right? This is all. Okay? And I can get this equation from the dynamic boundary condition. Okay? But once you evaluate this, give you this. Once you evaluate phi2, you get this. Okay? And usually, as you can see as before, dynamic boundary condition give us what? Give us dispersion relation, right? As you remember, what's a dispersion relation? Dispersion relation. And dispersion relation relates what? Relates the lambda c, right? Okay, wave speed and wave length. Okay, and also, so this is right now our lambda is a sigma, our lambda is c is sigma, right? C is a sigma. So we have sigma r and I sigma id, right? So this also represent our sigma to our lambda as our dispersion relation. Okay, so after we evaluate this, okay, we can get sigma is function of lambda. Okay, that's a dispersion relation. Okay, I think we'll take a 10 minutes break. Okay, after back we can finish this for this course.